now it was not.
Sorry? Aha. Once again, should I thank the organizers for this opportunity to speak here? The plan, as the title suggests, I'm going to tell you about two, say, open problems. So there are two for 1 hour. So in each case, I want to give you some motivation, side remarks, and partial solutions. Okay, so let me start. The first part is about embedding Boolean algebras into P omega mod finite. Okay, so this kind of subject always starts with Solovichenko theorem. And it says that if we have a Boolean algebra A, which is of size at most omega 1, then it can be embedded in this algebra. And well, I try to enumerate those remarks just to keep the right order. So consider concrete example of A, which is the measure algebra. So we can think that the A is now Borel sets of the unit interval modulo the null ideal. So we conclude that under CH this algebra, actually every algebra of size continuum, embeds into P omega mod finite. But what is perhaps more interesting, Dow and Hart in 2000 proved that under open coloring axiom plus Martin's axiom, the measure algebra does not embed. Okay. And of course, I should mention that there is a easy class of Boolean algebras which always can be embedded into P omega mod finite. These are centered, sigma-centered algebras. So if A is then it is easy to see that this, in such a case, we can write this kind of embedding. Okay, so before I state the problem.
Sigma center.
Of some size, no?
Sorry?
Do you need some size
No.
requirement?
No, I don't think so.
They are always of size.
Well, simply, you see, sigma centers means that A plus is the countable union of alpha filters. So we can actually, I think we can, sigma center algebra we can embed into P omega. And then, so also to P omega mod finite. So in this sense, those algebras are trivial when we ask about the embeddings. So let me define some wider class of Boolean algebras. First, some notation and terminology. I will write PA over a given algebra to denote the set of all finitely additive probability measures on A. So this means that this is a probability measure which is finitely additive whenever we have two disjoint elements of the algebra. So this stands for probability additive Usually I write P here, but P might be confused with that P. So okay, and consider the following class of Boolean algebras which admit a strictly positive probability measure. So say that algebra is in this class, I call it SPM, strictly positive measure, if there is, in the sense, above sense measure on the algebra, which is and the strict positiveness simply means that mu is 0 only on the 0 element. So we have to write a small diagram. We have three properties. Those trivial algebras, sigma-centered. Then the wider class algebras admitting strictly positive measures. And still the wider class algebras which satisfy CCC.
Can I ask a stupid question? Why sigma center implies that the size is continuous?
Let us check. If you have an element of the algebra, we can associate to it a set, say, Fn, Fa, sorry, of those n such that A is in Fn. I think actually this is isomorphic embedding into P omega, because what if elements are different? That there must be alpha filter showing this. Okay. And the next point on my list is the result of Podolchevich. There is a Boolean algebra which is inside, we can put it inside P omega not finite, which is here but not here, meaning that and this result, well, is true in the ZFC. So now I came to the main point of this list. This is the problem. Is there So of course we can see, looking at the measure algebra. Measure algebra is the example of an algebra which admits a strictly positive measure, because measure algebra has this canonical measure defined. And it's easy to check that measure algebra is not sigma-centered.
Sorry, when you say measures are sigma additive?
No, only finitely additive. Let me stress here, and this, at least in the first part, by a measure I mean finitely additive measure. but well, in fact, there is some connection, because I think you can define this property saying that a measure Boolean algebra admits a strictly positive measure, it's equivalent to saying that it can be embedded into some real measure algebra, taking some kappa to the kappa model sets modulo null ideal. This follows from the Mahan theory.
This question is only interesting if CH is not true.
Well, I asked the question if it's true in ZFC. Yes, you are right. Yes, under CH we have an example. Well, under CH, everything of size continuum can be put.
Sorry, I can't read. What have you written after Dow and Hart?
Sorry, where?
2000.
2000.
2000. Well, this is actually this 2000. Dow and Hart, yes. This is the paper appeared in 2000. Okay, and I will tell you what I know about this problem. I mean, I was able with my students to show under some assumption, set theoretical assumption, the answer is yes. So this will be the remaining part of the section A.
What about CCC, but does not have a strictly positive measure?
Yes, this is a good point. I mean, I should say at this point that it's clear that this Todorczewicz example of this Boolean algebra is such that there is no strictly positive measure.
It is clear.
I should say this, but let me say it seems that it doesn't have a strictly positive measure. At least it's clear then there is no strictly positive measure under some set theoretic assumption. Anyway, this example will not give us the answer to the main point.
Under what extra set theoretic assumption?
Well, Todorczewicz example is that there is some construction involving kappa many objects in P omega, where kappa is the additivity of the Lebesgue measure. And if I assume that covariant number of the Lebesgue measure is bigger, then it's easy to check that in his example there is no strictly positive measure. Okay, so of course we can reformulate slightly the problem to the setting I'm going to work with. So we can ask, is there simply we want to work in P omega. So is there a Boolean algebra A such that it contains all finite sets and it's inside P omega with the two properties. And the first property, I just repeat that the resulting quotient shouldn't be sigma-centered. And so and I just slightly reformulate this requirement about the measure. So there is measure on this algebra such that here instead of, well, I just need to write this. And the point is that one can try to construct this kind of Boolean algebra by induction. So Okay. I hope I can erase this introductory part.
So, about what I asked, so about the CCC but does not carry a strictly positive measure. So this Todorcevich example you think might not would not be does not carry a strictly positive measure, but is there another example?
Well, Todorcevich gave an example of an algebra as in 26, which is CCC but not sigma centered. The question, so far, I don't know if we can answer the question if this algebra admits a strictly positive measure in ZFC.
But another
Under some assumptions, it doesn't.
It doesn't.
Anyway, cannot answer your question.
Yes, this is what I mean, but under some assumption it doesn't carry a strictly positive measure, so it's not the way. This Todorcevich construction is not the right way to answer problem, main problem in
yes, but I'm asking about another question.
Yes.
If you want something which is CCC but does not carry a strictly positive.
Oh yes. This was an old problem in the 60s, I guess. And then there was this famous Greifman example. Yes, this is. Well, this kind of construction now you can write within few lines. Some techniques, yes. Actually, here here between this property carrying a strictly positive measure and CCC, there is quite a number of additional chain-like conditions. Like, you know, the algebra can be decomposed and come to the many pieces. In each piece, there are at most n disjoint elements, things like this. Sigma finite CC, it's called, or something like this. And all those more detailed chain conditions can be distinguished in ZFC. Almost all, to be honest. By the way, this is not very useful, but the carrying a strictly positive measure is also a chain condition. This is also no result due to Kelly, but it involves the so-called Kelly intersection number. But it can be described in purely Boolean terms that there is a strictly positive measure. Okay, so I, of course, will not give you the whole construction. It's technical, but I want to mention the following point: that if we attempt at inductive construction, there is some problem that we need to assume something. So the idea would be like starting from canonical object inside P omega and carry out some construction and then finally take the unit. And this is of some length capital. And for A0, to define A0, we can do the following. First, we can copy clopen sets of the Cantor set, find isomorphic copy, say A0 prime, inside P omega, and then define A0 to be the algebra generated by those sets imitating clopen sets and finite sets. And then you can easily copy the canonical product measure on the Cantor set. Of course, in such a way that every finite set gets measure 0. No, this is nothing really. You just divide omega into two pieces and keep going in the dyadic manner, and you define the measure starting with here is one of the two, here's one of the two. Whenever you take any finite modification of the first part, it still has the measure 1 over 2. And then the crucial thing is the following lemma. Like a Boolean algebra A, I shouldn't call it A, but okay, let me call it B, because A was this final result. Such that it contains this first A0 and suppose that there is a measure mu on this Boolean algebra B, extending this mu0 and having this above property, so such that mu of A is 0 if and only if A is finite. So this is some stage of reconstruction. We have some, but then still this algebra B. Imagine that this algebra B doesn't satisfy the first property when you take the quotient is sigma center. So imagine that we have a sequence of alpha filters on this B. And the lemma says the following: and there is infinite subset of omega such that this measure we have can be extended to the algebra generated by B and this new element. I should write the new Nash. And we preserve this property so that for every B and moreover, the idea is that I want to kill the possibility that those alpha filters will be in the future dense sets in the remainder. So it's enough to write the following. For every n there is a divided alpha A times okay, and I forgot about the essential thing. I cannot do it for every Boolean algebra. I can do it whenever the size of the is smaller than one. Well, this assumption is needed because this is sort of difficult to control what happens in the extension. There are many new elements and all should get the positive measure. So you need to control this and then you can do it and it's clear if the lemma is true, it's clear then we have a solution to our problem if B is continuum. So the first conclusion is if B is continuum, then there is
B you could relax to just require that I intersection x is finite?
I'm sorry?
You could relax it to ask A intersection x is finite or not?
Yes, of course. Yes. Those alpha filters are more principal.
Ah,
Then there is A in P omega, S in S in A. Because you can carry out this construction of length continuum, and you can kill all the possible candidates for the sequence of alpha filters in the quotient algebra to be dense. But actually
You assume that B is countable something?
sorry?
You assume the algebra B is countable?
B is of size less than
Less than
B. But actually, you don't need to carry out this construction for the length of continuum. So if you want to examine this kind of argument and we get a slightly better result, I mean, we could weaken this assumption to the following. Take this is popular name for the following ideal. The ideal of subset of the unit interval such that the closure has measure 0. And let kappa 0 be the covering of this idea. And let kappa 1 be the cofinality of countable subset on kappa 0. Now I can write the following, that instead of assuming this item, it's enough to assume that kappa 1 is not bigger than B. Because well, this ideal, well, you don't actually need to kill all the possible sequences of alpha filters. You can group it to some sets and then kill it and carry out this construction of length kappa 1. So if you are still below B, you can do it. And that's everything I know about this problem. So let me just. So not only if B is continuum that you have a positive answer, but also when what is the other situation? This ideal was considered by Bartoszyński and Michela in the 90s. So I guess what are the other possibilities for kappa 1 being small is that I think if you assume that the covering number of usual null ideals for the Lebesgue measure is omega 1 and B is also omega 1, then it follows that kappa 0 is omega 1. So from that we get that kappa 1 is also omega 1. Under this assumption, no matter what B is, we have also the answer. Okay, so this is this. So to summarize, the question is: can we solve this problem number 7 in ZFC, or otherwise, if there is a model set theory where there are no such examples, I think that this might be difficult to get because even this proof of Doe and Hart that under OCA the measure algebra does not embed it is quite subtle.
And this number in the Sachs model, this number is small, and you know, right?
Which one?
Well, like B is not equal to the continuum would be the Sachs model. But then I guess this number would be small and
Perhaps. I didn't inquire in my
it's because there's this covering, whatever it's called, the Saxion Minkowski. So I thought you maybe would.
Yeah, but the point is that this ideal is not quite the same as the usual null ideal, because the point is that if you have any set of measure 0 in the unit interval, then normally you need D sets, closed sets to cover it. So somehow it also depends on D.
I see. But I guess D there is also small. Yes, use the natural candidate.
Okay, so if there are no further questions, I will erase the blackboard because
But just one remark, nothing very deep, but you could imagine actually two examples that one works if B equals C and another works if B is less than. I mean,
yes,
there are things like that, right?
Yes,
so
yes.
that could say,
it would be very nice to get this kind of. Well, simply the only technology I know to get a Boolean algebra with a measure is just to define it by using your hands. And then this means inductive construction, and then there are problems. Okay, so I will
So
To
about
imagine a
this-
model.
sorry.
Well, about this kappa 1, so if kappa 1 is less equal B, then you have this, but do you know if this is sometimes not true?
Yes, I guess yes, because well, actually, I think this is in this Bartoszyński Shellac paper. I think they have a model where the covering number of this ideal is large. Okay, so.
Did that model B is equal to C? Or not? Is it in their model? Do you know if B is equal to
No, I
C?
don't remember. Somehow I got the conclusion that it's well, with this kind of technology I cannot solve in CFC. Well, the second problem, I should say it's perhaps let's say less attractive, but I'm going to give you some motivation. The main motivation comes from functional analysis, but I will skip it. Okay, this part B is I will consider now this set of all probability additive measure on a given Boolean algebra. This is a compact space because you can see simply you can think this is inside and being additive is a closed property. So this is a closed subset of some Tikhonov cube. And I mean, when I speak of some topology here, it refers to this subspace topology. But this is just a topology of, say, pointwise convergence on elements of the Boolean algebra. Again, this is an independent enumeration. Let me recall the following definition. Take any topological space. We say that the space has countable tightness. If property of the closure operator. So for every subset of X, for every point in the closure, there is a zero countable subset of A such that X is in the closure of A0. One definition. Also, I need to define another thing, which refers to properties of the measures in Boolean algebras. So take now take any Boolean algebra A and any probability additive measure, and I will define something which might be called the Mahram type of the measure. So Mahram type of this measure mu will be the minimal size of subfamily, or it can be taken to be subalgebra C, which is dense with respect to symmetric difference. It means, okay. And let me explain what it means. This means simply that for every element of the algebra there is C, sorry, for every epsilon there is C in C, so that the measure is of the symmetric difference is smaller than this. Well, this is how we define Mahram type of real measures, and then we have this one structure here. Let me just note that this kind of function, if you take pair A, B and associate this pair, this value, this is a pseudometric. So in a sense, I'm asking what is the density of the algebra with respect to the pseudometric. For instance, this means that saying that the Mahram type of a given measure is uncountable, this simply means the following. There is a family A alpha less than omega 1, inside algebra such that for every there is epsilon such that for every alpha beta different, and the measure symmetric difference is bigger than x. Okay, so now with the two definition I can write conjecture. This time I will call it conjecture because some probability is true. And this is about okay. Take this topological space, all the probability measures in a given algebra, and assume that this space, this compact space, has countable titles. And then we ask, does this imply that I think it's not quite a bit technical, so this is why I'm going to spend some time explaining the context. Okay, but this is the implication of the following form. I assume some global topological property of all the spaces of measures in a given algebra, and I want to conclude that all those measures on this algebra are small in the sense of the Maharon type. Okay, so just to give you, to illustrate that some of these kind of connections are not that difficult, is the following fact noticed by Roman Paul. And for instance, you can examine several topological properties of this compact convex set. So this here I say this space is first countable. If I don't leave, and there's something similar on the right hand side for every measure there is a countable family in A, which is dense from below, meaning that for every epsilon and A, there is C. So the C is inside A and the measure. It looks almost the same. Here, originally we considered a semantic difference. Here we want to approximate everything from below. So this is the model property. Okay, so some motivations for this conjecture. First of all, it's true on the matrix axiom. This is due to Kremlin. Let me just mention why it's true. So this is just the outline of the proof. The main thing is the following, that take a measure. I assume that there's a measure of uncountable type, so I take this measure and witnessing family. So with this property I mentioned before, so for every this is bigger than some side. And then on the matrix axiom, the conclusion is that this algebra must contain an uncountable independent family. There is independent is Boolean. And once you have independent family, you can define freely measures. I mean, if you have independent system in the Boolean algebra, you can say that first three elements get measure 1 and the rest gets measure 0.
What is independent?
Independent every okay, independent for every S finite subset of indices disjoint. If you take B alpha from S and you take B alpha from T, but here with the complement, then it's so if you take any finite
Boolean combination.
this is no moment. They are free in this Boolean sense. So if you have independent, you can define easily a sequence of measures. Measure alpha will be so that it gets on those elements gets measure 1 up to some moment and then 0. And you define this sequence and you show that the tightness is uncountable very easily. So this is one motivation that it's true under Martin's axiom, but I suspect it might be true with UC. And another motivation is that omega 1 is easy in this context. This is all resolved into telegram. So it must be from the 80s. If we move, here is the conjecture, if we move the cardinal up here, this is something true. So I mean, if the tightness is not bigger than omega 1, then already measure this Maharan type. And this is true in this.
What's special about omega 1?
Yes, I think I can explain. So the point is that we argue by contradiction, we assume that the Maharan type is omega 2. Then we can represent this whole algebra we can embed into the border sets of 2 to omega 2 modulo the null ideal. And then we use this fact that every element from A is in fact described by countably many coordinates. And then we use high-null free-set theorem. This is the main.
So actually it's omega 2 that's special, not omega 1.
Well, this is formulations.
Yeah.
So what do we use about omega 2 over here?
High-null, this is called high-null free-set theorem, right? If you take on omega 2, if you have a function which associate to elements some countable set which does not contain the element, then you have a very large independent free set, and that's the point. So this is true what Minna said, that what is special is omega 2, below omega 2 we have omega 1, while with measures and elements, usually they require only countably many objects to describe.
Is this somehow related with this Fremont algebra?
Yes, this well, actually, this was part of a whole line of investigation concerning Banach spaces, compact spaces measures, Haydn problem, and
Haydn problem.
and Polchinski conjecture. Yes,
But there you have some counterexamples on the C. So what happens here?
I'm sorry.
The Haydn-Fremont problem, you get an easy answer for omega 2 because of the phenomena just like this, which you called Haydn-Fremont. And you get a positive
Yes.
answer for omega 1
Yes.
and MA, and the negative answer on the CH.
Yes, you are right. But you see, the point is that if you just, what is relevant is this Kuhn construction of compact L space, for instance. This is in this kind of object. But in this, for this space, the tightness of the set of measures is uncountable.
I see.
So this is not a
Oh, I see.
counterexample.
So you
but
cannot
this-
get
no,
this
no, no,
kind
no.
of
That's the
measure.
point. Okay, so I try to. Actually, also I will perhaps not have time to mention this, but also the motivation for this conjecture comes from considering Rosenthal compactor and measures defining Rosenthal compactor. Let me just mention also the result of plot building Mozilla. In this context, In turn, this is just a remark. Well, what is the outcome of this fact? If we assume that every measure has countable type, then actually we cannot reverse this implication, but we can say something weaker or stronger in the sense it means we conclude that this space has d delta points. So not all the points perhaps are g delta, but there are many dense set of g delta points. And so the corollary is that whenever conjecture is true, then we have the following, that this compact of the form probability measures on some Boolean algebra has this property that from the very fact that the tightness is countable, we can conclude that it has g delta points. And in general, for compact spaces, you need some maximus to get.
What is a g delta point?
Well, this is just a point which is intersection of countably many open sets. But in the compact space, it means that there's a countable local base at this point. Okay. And well, why I said for me this is a conjecture, because I have the following partial results on this. And this is a theorem due to myself and Daniel Sobota. Perhaps I will need more space for the final result.
Is this the student you mentioned in the previous context?
This is present. This is student of Grzegorz Plebanek. But he used to be in Wrocław or something. So theorem is the following. I cannot solve it as it's stated, but I can do the following. Instead of taking a single Boolean algebra, I will take its free product. So I take the free product, probability measures on this Boolean algebra, and I assume that this tightness is countable, and the conclusion is the right one. And this at least was a nice way to prove the following result, the long history. I will, but just to warn you, now I already skipped to say that I consider measures on compact spaces really countably additive measures. So there was the old result of Boolean. Let me put it. This was in Boolean's thesis, which I found somewhere, but thesis didn't contain the result, but the remark that can't prove. So the first published proof by Podolczewicz in his paper pointwise sets of very long functions. And this is the result is the following: that if K is horizontal compact, then well, I just changed the terminology, but you can think that K is zero-dimensional. In such a case, we can still speak of those finitely additive measures on Boolean algebras as countable. I mentioned this because of course you may wonder, well, what are the natural examples of topological spaces, for instance, for which this corresponding object has countable tightness? The space of measures, and these are horizontal compacta. So horizontal compact is a space which can be seen as a subspace of very one functions on some Polish space, with the whole rest of Polish. And using this result, we get that theorem because this will be sloppy, but let me just state the following. If K is horizontal compact, then the product K times K is also horizontal compact, and the space of measures is also horizontal compact. This was proved by Dr. Dewar. Okay. So it's 4 o'clock. Thank you very much.
So is it true also for the cardinals? P of A has
Yes.
And it's true for such other cardinals that the space of all A such that P of A is equal to kappa, is kappa countable, but has the analog of this kappa doesn't have a universal object. And to give a motivation why I asked this question is that yes. So this Piotr and I proved that every such A embeds as a subalgebra to a Jordan algebra. And we were looking for something analogous of that for larger dimensions. And we couldn't find an analog of the Jordan algebra for higher dimensions.
I'm not aware of such an analogy, but perhaps this is something that might be investigated. So there is no German, so I let you close this.
Let's not let you take the speaker.